Good morning, everybody. I'm Bhargav, and this is Jeff.
I'm Jeff.
We are researchers from Web3 Foundation, and today we'll be talking about censorship resistance and how we plan to improve censorship resistance in Polkadot's Collator protocol. So this is joint work with Alistair, who is also attending the summit, and the engineering team at Parity. OK, so what's the agenda for the talk? I'll try to define censorship in the context of blockchains, kind of like narrowing down the scope, and talk about the approaches that people have taken, projects have taken for mitigating censorship, and then come to the point of like how censorship resistance connects with Polkadot Hub and the migration, which is like scheduled soon. And in the end, give an overview of our solution without really going into the technical details. So yeah, let's get started. We can all agree that in the digital world that we live in, censorship is quite prevalent. Be it government, be it big tech, they all have their like tools and techniques to censor content and information flow, right? So here I have a picture where like I'm pretty sure the I'm feeling a bit censored button would be pressed a lot more than I'm feeling a bit lucky. And the point over here is that there's, of course, like the law of land. So like, for example, like hate speech needs to be censored and so on. But there is no way of knowing whether like these entities are overreaching their power to censor content more than what is like really required by law. And somehow there is this misconception that like blockchains are like the silver bullet, and you introduce blockchains and you suddenly get rid of like censorship. But this is not really the case, right? So here I have like a screen grab of from the MEV Watch webpage. And as you can see, more than like 45% of the blocks on Ethereum after the merge are like actively being censored. So by OFAC, I mean it's basically a blacklist by the US Finance Department of the organizations or like users who need to be like censored for them to be like OFAC compliant. And more than like 45% of the blocks being produced on Ethereum right now are OFAC compliant. Right? And yeah, so let's like try to define censorship in the narrower scope of blockchains. So traditional censorship is like government or authority preventing information dissemination, right? So it has like a really wide scope. But in the context of blockchains, we would want to like focus mainly on like the ability of an entity, like let's say miner, a validator, or a sequencer on a layer 2, to prevent the delay of inclusion of a valid transaction into the chain. So it's either like preventing the transaction or delaying. So like the take note of the point over here of like delay of inclusion. This is something that is very specific to like blockchains. So it's not just preventing, but even delaying can have like consequences on the censorship of the transaction. And why is it a concern? It mainly undermines the decentralization and permission principles, which are like the key USP of blockchains, right? It undermines the credible neutrality of the network, which is one of like the flagship features that blockchains want to introduce. And the other thing is like the protocol security also can be compromised. So for example, like on Polkadot, the network upgrade happens democratically through all the stakeholders voting on the upgrade. So let's say there's a security patch, and people are voting on whether the security patch has to be updated or not. And if you have a censoring mechanism which is censoring all the A votes and only letting in the nay votes, then you are having a issue with like the security patch not being like updated, right? And more importantly, like in most like DeFi applications and so on, censorship can lead to like economic manipulation. So there's like a lot of like MEV to be extracted. Uh, let's say you are like trying to bid in an auction, and if your like transaction for the bid is censored, then you're at like a potential financial loss, right? So I would like to give like a very high-level taxonomy of the kind of censorship that is like prevalent in the blockchain space. So I've tried to like categorize or like classify censorship among like 3 different axes. So the first one is what I call like weak and strong censorship. So by weak censorship, I mean that the transactions censored are like temporary, and the inclusion latency is in like minutes or hours, right? So for example, you have like a buy order on a DeFi dApp, and the buy order is being censored to manipulate the price. And on the other hand, like strong or like more permanent censorship is where like this inclusion latency is like much higher. Here you can think of like, yeah, the validators colluding all together to like censor OFAC blacklists and so on, right? The other way of like classifying this is like some censorships can be like targeted and one-off, so you're like really targeting a particular user, or it could be like systematic over like a long window of time. And the third way of looking at it is whether it's like local or global in some sense. So the censorship could be really at like the application layer. So think of a dApp that's like filtering out certain users, or it could really be at like the protocol layer itself, like the core infra layer. And we are mostly concerned on the second kind of censorship over here, because this is what really affects like the protocol security. And I want to mention that things only get worse on L2s, right? Because most L2s have like a centralized sequencer. You can like check out L2Beat. Like most of the L2s right now run on centralized sequencers, and this is really a single point of failure because like this sequencer has the ultimate power to include or not include a transaction, like censor it or not. And yeah, now I want to get to like the kind of like techniques that are already in the literature to counter censorship or like to mitigate censorship. And there are quite a few technical mechanisms over here, right? So one of them is like encrypted mempools. So you want to like encrypt your transaction so that like the validator who is like deciding to include it or not doesn't know what exactly is there in the transaction. But these techniques have like, yeah, like technical limitations and don't scale so well. The other approach that has been taken is like inclusion lists. So Fossil is like one of the approaches that Ethereum is planning to take, where the validators are forced to include a particular list of transactions. So let's say like some transactions are waiting in the mempool for long enough, then the block is not considered valid if it does not include these like transactions which have been like waiting in the mempool. The third is like kind of baking in censorship resistance into the consensus mechanism itself. So there's a line of research looking into order fairness consensus mechanisms. So these are consensus mechanisms which also guarantee that the transactions that are being like finalized are first in, first out. So basically, the transactions which get into the mempool early are also finalized early. But this, again, has scalability limitations. Or the final approach is like, yeah, just like adding like privacy layers at the network level itself, so that like the validators really are not are kind of in the blind of like who is exactly generating the transactions and hence are not able to censor them. Right? And in an orthogonal technique here is like incentive-based mechanisms. So here the idea is that you want to align the incentives of actors in the network with censorship resistance, right? And this was like one of the approaches taken by Ethereum when it introduced like proposer builder separation. So one of its like intentions was to reduce censorship resistance. But funnily enough, it actually resulted in more censorship, right? So the point was that once you split the task of block production into a block builder and a block proposer, the block proposer only knows the header and not the content of the block, and hence is not able to censor. But in this process, you introduce these relays, centralized relays, and that opens up a marketplace for censorship. So there are some relays who claim to be OFAC compliant, and the block proposers now can directly get in touch with these relays and only produce censored blocks. So the point I'm trying to make here is that getting these incentive-based mechanisms are really difficult. Getting them right is really difficult, and that's why we would want to have censorship resistance at the core protocol level itself. And the other point is that all of this kind of is, at least in the PBS model, all of this is off-chain. So then there's again no accountability on what the centralized points relays are really doing. Yeah, Jeff?
Okay, so right, so we're going to tell you about a particular case of this. So an overarching piece of the story that Bhargav was just telling you is that when people, what commonly happens is people look at the problem and they try and sort of solve the whole problem. They design something very complex. It doesn't actually solve the whole problem. They design something else very complex, et cetera, et cetera. Usually what we do that is a bit different in Polkadot is we figure out how much of the problem we need to solve. And so okay, so what I'm gonna, okay. The original idea of Polkadot was that most of these censorship problems would well, of course, we would always have, we knew from the beginning that we were gonna have censorship problems both at the parachain level and at the relay chain level. And we put some measures into the relay chain design, into how that protocol works to mitigate the problems at the relay chain level. That's why, for example, we have 5 backers instead of just 1. So the original design of Polkadot was basically saying the parachain is responsible for its own liveness and for its own properties like censorship resistance, and the relay chain is responsible for problems like safety and things like soundness. Now, the thing that we discovered once we were actually, that was there baked in from before. That even sort of, something akin to that even came from Gavin in the very beginning. But it was quickly recognized by Al early on. That it was what we wanted to do. Okay, so then now we had all of this stuff like the balances and the staking and the governance on the relay chain, and what we noticed when we actually designed Elves, when Rob Habermeyer, Alistair, and I designed Elves, what we realized, and then once everybody did the security proof on it, is that we actually had almost as much security on a parachain as we do on the relay chain. The only difference in the security there is really the assumption of this very technical assumption of synchrony on one message type, and some kind of balance type assumption, or some kind of economic assumption. But so there's not much difference in the security between a parachain and the relay chain. So what this means is that we can move stuff off. We can move whatever we want off of in principle, we can move whatever we want that isn't actually related to running the parachains off of the relay chain and put it on a parachain. This means that we can free up. This has a few effects. One, it means that we're now building at parity in Web3. We're building a parachain, which makes us behave better, perhaps. But it also dog fooding. But it also means that we free up a lot of compute time on the relay chain for doing other more important stuff. So it's about a 30x improvement in that. Well, on Kusama scale. Okay, so now the problem with this is that there's the collators. Then the collators of these system parachains that we're creating, things like Asset Hub, then become their liveness then has consequences for everything else that can happen on the relay chain, in particular stuff like upgrades. So it means we have to take this liveness problem more seriously, this thing that we sort of said, well, parachains will deal with it, that we have to take it, make this, and censorship resistance. We have to take it more seriously. So now we have to solve the censorship problem, but we only have to solve it well enough for all of the critical systems in Polkadot that were on the relay chain that shouldn't stay on the relay chain. So the setting we're going to be dealing with is we're talking about system parachains. They're still going to be using Aura. This is round-robin block production. We're going to assume at least one collator for that is honest at all times. This is, of course, not true in general, but not at all times. We assume at least one collator is honest often enough, and because of the way the collator, so not one collator. This means one backer. One collator is honest at all times. This we have to assume for obvious reasons. We assume one honest backer. This is not true all the time, but with the rotation, it's close enough to true. It can be true often enough for the kind of stuff that we're talking about doing. We're assuming all the other stuff that exists in Elves, like the data availability layer, and now, here's some design constraints. We don't want to throw on a bunch of complexity, like all of these systems that are appearing in the Ethereum world. We don't want to introduce slashing for collators, and it would be nice, and because we're keeping this thing simple, it will somewhat generalize. But again, it's not designed to solve the entire censorship problem. It's designed to solve, the one that, the things where we actually have to deal with them. And in particular, the setting we're in is we can prioritize transactions because we can assume that anything that's a smart contract doesn't actually matter. It's all the stuff that's kind of baked in that has to run. So Aura is this round-robin block production. Now, there's a general problem that round-robin is weak against censorship attacks. This is why sassafras is interesting, why we're doing that. That isn't the problem we're solving here. The problem we have is more something akin to selfish mining. And I'm not sure if people know this, but like Bitcoin will eventually collapse under selfish mining. There's a nice theorem from some people at Princeton at that. So the specific attack is that malicious collators can time their block production when they produce their blocks in their slots to try and squeeze out an honest collator. So this is, in addition to the problems of round robin, this is something that makes it work. So the honest path, what should happen is everybody builds on the guy before them and kind of in the middle of their, at the appropriate time in their slot. What the attack is that A delays building until the end of his slot, and then C builds directly upon A. So this is basically selfish mining. And the idea, and the problem that Polkadot creates very specifically is that because A doesn't give his block to B, B can't build on it, and that because the block is now has now been backed on the relay chain, it will B is not allowed to build on anything except A's block, so B must go through the reconstruction from the availability system. Okay, or at least get it from the backer. So that means that B is slowed down in even obtaining the block from A, and if that slowing down is bad enough, then C can build early on A and get his thing backed. And they're screwed. So what we have to do is we have to change the correlation protocol and other aspects of the protocol so that to give B a little more time to reconstruct his block. So there's a few things. We discussed a number of different things. Ultimately, what looks like the optimal solution here, what seemed to be the optimal solution, is simply we give every collator, we make every one of them produce a number of blocks in a row. So instead of round robin, it's I get 4, I get 4, I get 4. So it's round robin with 4, with 3, 4, 5 in a row. And what happens here is B now sees that he doesn't have the things from A, so he starts reconstructing. And he, maybe A doesn't even give him the first block from A's thing, but he has time to do that reconstruction. And so the point is that B will be able to basically, the point is that because of this extra time, B will have more time to catch up, even against the very last block in A. So, and what we want is that B can produce 1 block in his thing. So instead of getting 5, he'll only get 1. That's still a form of censorship, but again, we're going to be able to prioritize what goes in the blocks, so it doesn't, on something like Asset Hub, so it doesn't matter. It's good. It's plenty good enough. Yeah, and so that's so there's a few things we swept under the carpet here, like obviously the protocol has to be somewhat more complicated to deal with all of these multi-block things we're doing now, like async backing, elastic scaling, and the BASTI blocks. There's there's always a tension between I would have said between like elastic scaling, going faster, and censorship resistance. So, that's inherently a conflict. But and the how we actually get the block is a little bit different. But there's some other things like the timing of blocks. We figured out that we can make the block timing mechanisms much less dependent on wall clock time, which is very cool. Yeah, and I think that's it.
Thank you.
Questions?
Yes, I can pass around the microphone if there are any questions. We do have a bit of time because, where is it? Which one? Where? Where is it?
I don't know.
No. Do you see it? Anyone? We have a bit of extra time because the next speaker has not arrived. So
okay.
I don't know if you want to go, there's other thing you want to go through or,
Yeah, let's see. So, I mean, I guess I just wanted to say that it's important in this setting when you're designing protocols to understand what the problem you're actually trying to solve is. People really, you can really come up with some wild shit when people think they're trying to solve everything and they try and solve it in isolation. It's cool academically, but it's much better in terms of optimizing. I mean, this thing we're proposing, adding a few blocks and then there's a bunch of small tweaks we did brush under the carpet here, but this is a much simpler protocol change than something like all of the things that Bhargav mentioned in the Ethereum world. Is there anything else?
Yeah. And I guess maybe like one more thing that we would want to mention is basically like how do we pick the number of slots that you consecutively give a collator. And here again, there's a trade-off. So you want this number to be high enough to avoid censorship, but the lower the better because it affects liveness. And we kind of derive this basically based on the protocol parameters of async backing. And the value over here is basically a minimum of two values. And in some way, the async delay helps us in reducing this number. And with our calculations right now, this is basically 4 or 5 consecutive slots per collator.